2.2, Evaluate and Graph Polynomial Functions. First, let's look at what polynomials are and some terms we use in discussing polynomials. A polynomial that has only one term is called a monomial. Monomials consist of a number, a variable, or a product of numbers and variables. Something like 3x squared would be a monomial, or negative 5x cubed y to the fourth. Polynomials then consist of either a monomial or the sum of multiple monomials. Something like 3x squared minus 2x to the fifth plus 7 would be considered a polynomial. Polynomial functions can be written as the sum or difference of multiple terms. This x to the n power would represent the highest exponent and power in the whole function, and then the a sub n just is the coefficient that goes with that term, or with that factor. And then notice the a sub n minus 1, that's just going down, although the value could be anything here. The x to the n minus 1 power just shows us it's the next power down in order. Now we could skip over powers. It could skip from the fifth power to the third power, but usually if it's written in standard form, as I talk about down here, standard form would be the terms are written from highest exponent to lowest exponent. The exponents in polynomials have to be whole numbers. The coefficients are real numbers, and those are the numbers that are in front of the variables. A sub n is called the leading coefficient. It's going to be the number that's in front of the variable with the highest exponent. N, which is the highest exponent, is called the degree of the polynomial. So, for example, up here, 5 is the highest exponent, so we would call that a fifth degree polynomial. And because it has 3 terms, we would even call it a trinomial. A sub 0, represented up here at the end, is called the constant term because it doesn't have a variable with it. In my example up here, 7 would be the constant term. Not all polynomials will have a constant term. Here are some common polynomial functions. A polynomial that's a 0 degree is called a constant polynomial. An example of that would be f of x equals y. Now remember, f of x is just function notation. That's the same as saying y equals 5, and that would graph as a horizontal line. Now the reason we often use function notation is that it shows that we're plugging in values of x. Well, if it's a constant, x could be absolutely anything. Just y has to be 5, creating a horizontal line. Then if we go up a degree to first degree, it creates a linear function. An example of that would be f of x equals 3x minus 2. And you might recognize that function as being in slope-intercept form. Its graph would just be a straight line, but slanted. Since this one has a y-intercept of negative 2, if I were graphing, I could start down at negative 2, and a slope of 3, I could rise up 3 over 1 as I graphed it from there. Again, creating a line that rises to the right. A second degree polynomial is called a quadratic. And you might remember we did a lot with quadratic functions in the last chapter. Quadratic functions would graph as a parabola. This one has a positive leading coefficient, so that parabola would open up. Then a third degree polynomial is called a cubic. So we can see this one here, an example, has x to the third power in it as the highest power. And it's going to graph something like this, where it goes up, then usually back down, then back up. Now, the turns you can sometimes distinctly see, other times it just kind of flattens out. A fourth degree polynomial is called a quartic function. Example of that would be f of x equals negative 5x to the fourth, and it would graph something like this. Kind of like a parabola, but more turns. Now, later we're going to talk more about end behavior of these graphs. And what end behavior means is what is happening to the graph as x approaches positive infinity and as x approaches negative infinity. Well, if I look at this one, as x approaches positive infinity, we can see the function is going down, and it's going to keep going down. So we would say that the function is approaching negative infinity. Then as x approaches negative infinity, going to the left, we would say that the function f of x is approaching negative infinity as well, because it's going down infinitely. You can see, in this case, the right end behavior and the left end behavior are the same. Versus our cubic function up here, its right end behavior is going up, so it's approaching positive infinity as x approaches positive infinity. But then as x approaches negative infinity, the graph is going down, so we would say the graph is approaching negative infinity. So its left end behavior, approaching negative infinity, is opposite of its right end behavior, approaching positive infinity. We'll talk more about end behaviors later. Based on our definition of polynomial, let's play a game, polynomial or not. As we look at these functions, let's decide whether the function is a polynomial function. If so, we'll write it in standard form and state its degree, type, and leading coefficient. Function number 1, polynomial or not. We'll look back at your various properties for polynomials. It says the exponents have to be whole numbers. And right here I see an exponent that's not a whole number. So that means it's not a polynomial. Let's look at our next function, g of x. As I look through this, I see I have real numbers that are coefficients, negative 8, negative 4, 1, a constant that's a real number as well, square root of 10, and I also see exponents that are whole numbers, 4, 2, and 3. So this is a polynomial. To write it in standard form, we need to start with the highest exponent. It'd be negative 8x to the fourth power. Then I would have x cubed would be next in line. Then the x squared. And then the constant, which is square root of 10. It's okay that our constant or coefficient is not a whole number, it just needs to be a real number. The degree of this polynomial would be fourth degree, because we can see the highest exponent here is a 4. It has 4 terms, so we could call it a 4-term polynomial, and because it's fourth degree, we would call it quartic. The leading coefficient, I want to look in front of the x to the fourth, so the leading coefficient is negative 8. Our next function, f of x equals x cubed minus 4/5 x squared minus 1. What do you think? Is it a polynomial or not? It is a polynomial, and it's already written in standard form, starting with the highest exponent, going down to the next, and then the constant. Now notice there's no x term here, and that's okay. I could add plus 0x, and it wouldn't change the value. The degree of this polynomial would be third degree. I can see that the highest exponent is a 3. The type then would be cubic, because it is third degree. I could also call it a trinomial because it has 3 terms. The leading coefficient would just be 1. Because I look in front of the x cubed, and even though it's not shown, a 1 would be implied. I only have 1 x cubed. And our fourth one, h of x. Check it out, polynomial or not. Well, as I look through the exponents, I see one right here with a negative. Our exponents in polynomials all have to be whole numbers, which would be 1, 2, 3, 4, etc. Negatives, zeros, not included. Actually, 0 is a whole number, but we learned that anything to the 0 power equals 1, so we really wouldn't show anything to the 0 power. But again, because this has a negative exponent, it is not a polynomial. We can evaluate polynomials in a couple ways. One way is using direct substitution. This will be the most common and the one you're probably already most familiar with. To evaluate this function, when x equals 2, we just want to plug in 2 wherever we see x. An advantage of function notation is that I show what I'm plugging into the function. So f of 2 means everywhere I see a 2, I'm plugging in x. So I can take negative 3 times 2 to the third power plus 2 squared minus 12 times 2 minus 5. Let's simplify that. Exponents come before multiplication here. So 2 to the third power would be 8. 8 times negative 3 would be negative 24. Plus 2 squared is 4. Minus 12 times 2 is 24. Minus 5. Let's add those together. Negative 24 plus 4 would be negative 20. Plus another negative 24 would get me a negative 44. Combined with a negative 5 would be negative 49. That's direct substitution. We directly plugged in what x equaled, and we found the value of the function. So we can write this as the function evaluated at 2 has a value of negative 49. I can see both the input and the output in one statement. The other type of substitution we can do is called synthetic substitution. For synthetic substitution, we want to start out by writing the coefficients. Negative 3, that's 1x squared, so I'll put a 1 next. Then negative 12x, so negative 12, and include the constant term of negative 5. Now, with synthetic substitution, I do have to be careful that if I skip over any powers, so if this skipped from x cubed to just x, and if I didn't have any x squared in there, I would need to put a 0 as a place marker. So that's one thing to be careful of here. Then, whatever I'm taking into that, whatever x equals, I'm going to put off to the side here and the little box, half box to separate it. Now from here, it's going to be a process of adding, multiplying, etc. Now I'm going to leave a little space here, and I'm going to draw a horizontal line. Because the sums are going to go below the line, the products are going to go above the line. So as I set this up, I'm going to first start with addition. Negative 3 plus nothing, I don't have anything there, is just negative 3. So again, the sum goes below the line. Then whatever is below the line, I'm going to multiply by the x value, which in this case is 2. So negative 3 times 2 is negative 6. That product will go right there above the line. Now I'm back to adding. 1 plus negative 6 is negative 5. Then multiply the negative 5 times the 2 up here, and I get negative 10. Then add negative 22. Multiply again by the 2. That gives me negative 44. And add one more time, and I get negative 49. Notice negative 49 is what I got using direct substitution. This last number will always be the value or the remainder when I plug in the 2. Now, at this point, synthetic substitution seems a lot trickier than direct substitution. But the concepts behind direct substitution we will apply later. So let's go over this again. With synthetic substitution, we first write the coefficients, -3, 1, -12, -5, and put in zeros for any missing coefficients, or even if I didn't have a constant term, I'd need to put in a 0 for the constant term. Then the value of x will go off to the side. That's the number I'll always multiply by. Then I start by bringing down the first number. So I'm adding -3 to nothing. I get -3. And then from there, it's a process of multiplying by the 2, putting the next number here, and adding it to the next coefficient. All the way through, I add, multiply, add, multiply, add, multiply, and my final number is the answer. Let's talk more about end behavior. The end behavior of a function's graph as x approaches positive infinity or as x approaches negative infinity is what is happening to the f of x values. Is the function going up and approaching positive infinity, or is the function going down and approaching negative infinity? Well, there's a couple of things we want to look at in the function to determine the end behavior. The first thing we want to look at is the function's leading coefficient. Remember, the leading coefficient is the number in front of the highest exponent, or the variable with the highest exponent. Now, the leading coefficient is either going to be a positive number or a negative number. And you might remember from parabolas, if our leading coefficient was a positive number, the graph would open up. If the leading coefficient was a negative number, the graph would open down. You might also remember with linear functions, if the slope is positive, the graph would rise to the right, so that would have a positive leading coefficient. If the graph had a negative leading coefficient, the slope would be negative and it would fall to the right. Well, what do these graphs have in common? If it has a positive leading coefficient, the function's right end behavior is it's going to be approaching positive infinity, like this or this. If the leading coefficient is negative, then the right end behavior, again as x approaches positive infinity, well, the function will be approaching negative infinity. For example, this one here, going down, approaching negative infinity, and this one here. Now, this is only to determine the right end behavior. So looking at as x approaches positive infinity, what's happening to the graph as it goes to the right? And again, we call that the right end behavior. So now let's look at how do we determine the left end behavior. Well, for the right end behavior, remember, go back, we're looking at leading coefficient. For the left end behavior, we want to look at the degree of the function. Now, we already know that the degree is the highest exponent, and that number has to be a whole number. So what we want to look at with the degree is that whole number odd or even? Well, if the degree is even, then the graph will do the same thing for the right and left end behavior. So even degrees have the same end behaviors. Think back to the parabolas. They are an even power because they are x squared, so the degree is even, and has the same end behavior, rises to the right and rises to the left. Or, if it's a negative x squared, once again, we have the same end behavior, falls to the right and falls to the left. Versus if we have an odd degree, we're going to have opposite end behaviors. So something like a linear function is an odd degree, first degree, and we either have it rising to the right but falling to the left, or falling to the right but rising to the left. A cubic function will do the same. If it's rising to the right, it will fall to the left, or if it's falling to the right, it will rise to the left. So that's why we need to first look at the leading coefficient to determine the right end behavior, and then look at the degree to determine if the left end behavior will be the same or opposite of the right end behavior. Let's see how we can use end behaviors to help us graph polynomial functions. For example, if I want to graph the function, let's look at y equals negative 2x cubed plus 5x minus 3. Well, first of all, I can look at end behaviors. As x approaches positive infinity, I'm going to look at the leading coefficient to determine what the function is going to do. Because my leading coefficient is negative, I know that the graph f of x, or y, is going to approach negative infinity. That will be its right end behavior. Then I can look at the left end behavior and see as x approaches negative infinity, my function f of x, or y, is going to be, well, let's look at our degree here, and our degree is odd, which means it's going to have the opposite end behavior. So because it's approaching negative infinity, the graph is falling to the right, then to the left it's going to do the opposite of that. The graph is going to be approaching positive infinity. So it's going to be going up to the left. So in general, I know my graph should be going down to the right, up to the left, and then we'll probably have a turn in between. Actually, probably 2 turns. We'll look more about determining turns and all that later. Now, if my goal is to graph it, I can have the general shape in mind and then plug in some values to get where specific points are. Now to graph. I want to find some specific values on the graph. I know the general shape I'm looking for, but other than that, I don't know too much specific. Now, actually, a good starting place is going to be with the y-intercept. And the y-intercept will always end up equaling the constant term, because if I plug in 0 for x here and here, that just equals 0. So y will equal negative 3. So if I plug in 0, I get negative 3. And I can even put that on my table of values down here. And over on my graph, 0, negative 3, let's put a point right there. Now I want some more values on my graph. So let's plug in other values for x, see what we get for y. If I go down to negative 3, it'd be negative 2 times negative 3 cubed plus 5 times negative 3 minus 3. I'll plug that in. I can either use my calculator or evaluate that by hand, and then I'll put that value into my table. Go ahead and see what you get. I got 36. If you got 36 as well, go ahead and continue with the rest of the table. Plug in negative 2. Go ahead and pause, fill in the table, then we'll compare. For negative 2, I got 3. For negative 1, negative 6. For 0, we already had negative 3. For 1, you should get 0. For 2, negative 9. And for 3, negative 42. Now, if I look at my numbers, you can see I don't really see a pattern. It's skipping from positive values to negative values, back up to 0, then down to negative values. But again, it's going to give me a good shape of the graph. Now, I don't need to necessarily go all the way to positive 32 and all the way to negative 42, because I know it's going to keep going down to the right, and I know it's going to keep going up to the left. So let's plot at negative 2, that was at positive 3. So let's put a point over here on my graph, negative 2, positive 3. Then at negative 1, it was down to negative 6. So about right in there, kind of a big dot. 0, we already did -3. Then 1, 0, put a point there on my graph. And then at 2, -9. Now -9 is off my graph, so I know it's going to keep going down to the right from there. And it's going to keep going up to the left from this point. And pretty steeply, because it's getting at by -3, it's way up at +36. So I want to make that fairly steep. Then I can just draw it down to this point, and then it's going to need to curve back up to here, and then up to here and go back down. Now, without plugging in more values, I really don't know if it's going to stop at this point to curve back up, or it might actually go down further and then curve back up. All I know is it has to go through these points that I put on the graph. Now, because we're just doing a quick sketch and we're going to look at details of these graphs a little bit more later, this is a good graph for now. So you can see I can use the end behaviors to know it's going to keep going to the left, it's going to keep going to the right, and then it curves up and down from there. And that concludes lesson 2.2, Evaluating and Graphing Polynomial Functions. Thank you.